Hello, everyone. I'm Mounika, and this is Andreas. And our project is on roof segmentation for efficient solar panel placement on large area commercial buildings. So we both are really passionate about scaling green energy, and hence we chose this topic. And this project is in collaboration with a UK-based company called InRange, and their mission is to make local grids 100% renewable. So quick outline of this presentation, I'll go over the motivation and the primary goals, and then the implementation, which is which model we use, and then the most interesting part, the predictions or our results, and then the future directions. So coming to the motivation, we know that there's a huge demand for clean, renewable, and decentralized energy sources, and the most popular one being solar energy. And solar energy forecasting for large area roofs is primarily interesting because you can do that without on-site analysis if you can automate this process. And one of the key challenges for that especially is efficient allocation of solar panels on the given roof surface. And keeping that motivation in mind, our primary goal is roof segmentation. What I mean by that is basically if you have a roof, to segment it into its faces. We just have a few basic rules, which is not to place solar panels on the edges of the buildings because that's not efficient, and also to use the space that we have effectively when we place these modules. So for the implementation, we'll go over the pre-processing and ground truth. I just want to mention that one of the major challenges that we had for this project was there wasn't any established ground truth. So we needed to do that before we go forward, because as we all know, having a ground truth helps us with evaluating how true our metrics are later on. And then Andreas will go over the network architecture, and we use something interesting, which is active learning to build on this ground truth. And then we'll do the model evaluation. So what you see on the left-hand side is the original satellite image, which is basically a Google image, but a much zoomed in one on a large roof that we got from the company. And then we use a custom-built polygon crop function. What it does is basically outlines the building, so draws a polygon around it and just crops it and keeps everything around it a background pixel. So as you can see, I can only see the roof and all the background is in black. So this really helps with segmentation because then I don't have to label anything outside the building because my primary focus is on the building. So here's another example of one such building. Here you have like a couple of buildings together. So to establish the ground truth, we use label me. So what you see here are three classes. So everything in black is the background. So anything other than the building is what we call the background. And then all the interesting parts of the roof where we want to place the panels, which we call the facade here, is in green. And anything which is part of the building, but not a part of the facade, is an edge. So that really helps to outline the parts of the facade or the building, which is where you cannot really place a solar panel. This is just overlap of both these images just to show how to segment a building. So this is an example of the ground truth we established, and we start off with 25 images. Andreas will later on tell you how we just started with a small set and how he progressively built on that.
Okay, thank you, Mounika. As Mounika said, we only have really little data set and we created on our own. So we had to make sure that the model learns a lot from these small data sets. So we choose a lot of augmentations. We applied a lot of augmentations on the small data set, which ranges from horizontal flips, vertical flips, random rotations, zooming in, bit of noise, and so on. And a few examples of the augmentations we got from this algorithm you can see here. This is really helping the model to learn the invariance which is needed actually. So let's come to the architecture we used. We used the famous model unit, which is famous for segmentation tasks. And obviously, as we said often, we have a small data set, so we use the transfer learning approach. And for the transfer learning approach, we used different backbones like Resonant 34, Resonant 50, and SqueezeNet, and so on. And we figured out in an early stage that the Resonant 34 as a backbone is the most suitable one, which where we can get the best results in terms of metrics. So let's come to a really interesting part, which also goes in the direction of how to make the small data set most suitable for the algorithm to learn. So in the beginning, we used K-mediates algorithm, clustering algorithm to segment all the images we got initially to cluster into different segments or clusters. And then we choose from every cluster single images to label on. So in the end, we had, or in the beginning, we had 25 images, which represents the diversity of the whole data set quite well, actually. So, and on the bottom, you see like an example for 7 mediates, where you can see the images are quite different. Okay, let's talk about model evaluation. So as Mounika said in the beginning, we had initially 25 images, and we went up to 80 images using this cosine similarity K-mediates algorithms to get until 80 images. And in the beginning, we had metrics of one-score precision and recall around 91%. And we reached, after this active learning process, we reached over 95% for all these metrics. So in terms of accuracy, which is also really interesting or reasonable, actually, we reached 97% for the background, 95% for the facades, and 71% for the edges, which is also quite good because if you look at the pixel distribution or class distribution, we only have 6% of all the pixels are edges. So these are promising results. And now we come to the actual results. On the left-hand side, on each of these 4 sample images, you see the original picture. Then you see the predicted mask on a test set. And on the right, again, the overlaid picture. So what we got, we have effective roof segmentation of different slopes, as you can see in the top left picture, where different slopes with different angles are captured really well. We also captured shadows quite well on the roofs, which is always a problem in satellite images, depending on where the sun is standing, which was also in the initial trials, initial experiments was a problem. We got that. We also achieved that we separated different buildings from each other, which you can see on the left, bottom left. And also, which is quite nice, normally you have a lot of different stuff on the roofs, like windows, like small strips, like different colors and so on. And our algorithm is not affected by that. So it detects the problems on the roof. It doesn't detect the problem of the room. So it's not an object detection at this point. This is what we wanted to have. That's only a small number of really good examples, but we also have like worse examples, which will Mounika talk about now.
Well, these are great results. We always need things to improve on, right? So for the first example that you see there, the smaller slopes are not effectively captured. And in some examples here, the slopes don't go all the way to the edges. And that is kind of important because in the next stage, we're going to extract polygons to calculate the effective surface area. So if you have a hanging slope like that, it's not going to really detect a polygon there. And sometimes because of the overexposed image in that corner, it doesn't even detect a slope sometimes. And I would say in the entire data set, this is the worst prediction that we had. So it looks something like that, which is not that bad, I think. Okay, so this brings me to the future work. What can we do to improve on these imperfections that I showed you in the previous slide? One thing is morphological operations. So there's something called erosion and dilation operations that you could do. And as the name suggests, erosion would just remove some pixels of an object, and dilation would add or expand some of these pixels. So we applied these just as a proof of concept on some of our predicted mass, which are not so great. And this is what we see. So in the first one, you see that these slopes are not continuous towards the edges. So then after we apply these operations, we're able to draw continuous lines for those. And then in cases where the slopes are cut off, you have them continue to the corners and sometimes even to the edges, which we didn't see over here. There are continuous slopes that are detected. So this is a great post-processing steps one could use to improve these predictions. And one other thing which we didn't really have a lot of time is to use LiDAR data, because that would help to calculate the actual slope of the roof, which would then help to calculate the effective area of the roof. Don't have much time, but in summary, I just want to say that we had a lot of fun working on this project together. And yeah, so we'd like to thank Bernhard, who's from the company InRange, and Antonio at DSA for mentoring us. Thank you.